Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And salam sejahtera to all of you guys. How are you today? I hope today is your fine day. Okay, we continue with our chapter. This is chapter number 6, air conditioning, and in part 3. Before I start, I would like to thanks to my colleague, Dr. Azmi Hussein, because of his effort to provide this slide. Okay, now let's go, or let's look on the objective. Okay, the objective of your study for today. Okay, today we have only one objective to be seen. That means, okay, the objective you have to know is only one objective. This one. That means you must should able to apply the principles of the conservations of mass and energy to various air conditioning processes. That is your objective for today. So the content what we will discuss is about this one. That means today class, student you should able to know the basic processes of air conditioning. That means heating, cooling, humidifications, dehumidifications, and also adiabatics mixing. Okay. Okay. Before I go further on this topic, first of all, I would like to introduce to you what about introduce to you some important thing you should know before we proceed to this topic. Human being, okay, that means us, human being. We always want to feel comfortable. We like to live actually in the environment that is neither hot nor cold, neither humid or dry. So what we have to do to feel comfortable to our body, so we have to do something to the environment. But keep in mind, or as you all know, the environment is, I made example as a weather. Okay, weather in the area, in our area, we cannot change the weather of the area. So how we can solve this problem? We only can change it in the comfort space, such as the house or the workplace. That's only things that we can do to suit our comfortable of our body. Okay, so how we can do this? Today, as you all know, or as you all seen, the modern air conditioning system can heat, can humidify, also can clean, and even it can deodorize the air. In other words, that means the conditions of the air to people desires. So air conditioned system are designed to satisfy the need of human bodies. That means it is essential uh, that we understand the thermodynamic aspect of the body. The comfort of our human body primarily depends on three factors: the dry bulb temperature, the relative humidity, and also the air motions. Okay, these introductions I have introduced to you in earlier of this topic. Okay, so another factor that affect comfort of our body are air cleaners, outdoor noise, and also radiation effect. So that is for the introductions. How or why we must know, or we have to know the air conditioning processes, because you will become as an engineer in the future. So as the engineer, you have to solve or you have to serve to the people. That means you have to solve some technical problems. In this case, it based on the air conditioning process. Let's look on the air conditioning process. Okay. Uh, saturation. Okay. The air conditioning process uh, includes simple heating. That means rising the temperature. Simple cooling. Uh, it is lowering the temperature. Humidifying. That means adding moisture. And dehumidifying. That means removing moisture. Sometimes two or more of these processes are needed to bring the air to the desired temperatures and humidity level. You must notice that the simple heating and cooling processes appear as a horizontal lines on the psychometric chart, and the moisture contents of the air actually remain constant. That means specific humidity omega is constant during this process. Okay, that is you have to notice. All right. Air is commonly heated and humidified uh, in winter or in the cool day, winter, and at a cool day, and cool and dehumidified in the hot condition. Okay, hot day. So this you have to know or notice that these two two processes appear in the stoichiometric chart. Okay, as you see in the stoichiometric chart, okay, this is a stoichiometric chart that has we learned previous lecture. Okay, so here as you see, um, the cooling process is at left side, horizontal left side. Okay, and the heating process is at the right side of the psychometric chart. Um, so the humidifying is that goes to the top, okay, of the psychometric chart, and dehumidifying is going down of the stoichiometric chart. So as you know, this is a scale of this RH, or relative humidity. Okay. So what happened for the humidity? The phi, or relative humidity, will be increased, but for dehumidifying, the relative humidity will be decreased. Okay, or in this community chart, it also we can show two processes that will happen or can happen in the air conditioning. That means when we said heating and humidifying, okay, the process is at the right side, but in these sections, okay, the arrow will go in these sections, or when it show on the cooling and dehumidifying, the arrow will be downhill from this psychometric chart. Okay, this is cooling and dehumidifying. Most of the air conditioning processes we can model as a steady flow processes. That means steady flow. When we deal with steady flow, it means SFEE. Okay, steady flow energy equations. And through the mass balance relations, that's mean n dot in and then dot out, can be expressed for dry air and water. Okay, as these equations, the total of m dot a for dry air is equals to the total of m dot out for dry air, and the unit is kilogram per meter. So also for the balance of the water, okay, the mass balance for the water, that means the total in of the m dot water is equals to the total out of m dot water. Or this can be structures, or again these equations, the total of n dot water times the specific humidity is equals to the total out of n dot water times the specific humidity. That's mean omega. Disregarding the kinetic and potential energy changes, uh, and the steady flow energy balance relations, that's energy rate in is equals to energy rate out, that's mean energy balance, can be expressed as this formula. Okay, q dot in plus w dot in is equal to the total in of m dot h equals q dot out plus work dot out plus the total out of m dot h. Okay, this is we neglecting the potential energy and also the kinetic energy. Okay, please refresh back your thermodynamics, where in thermodynamics as a volume in the chapter of volume, steady volume, where we learn about steady SFEE, steady flow energy equations. Okay, this is the energy equations that we use in this topic. Okay, and one thing you have also to remember is the work term usually consists of the fan work input. Okay, uh, but this input is small relative to the other term of energy balance relations. So fan work input we can also neglect it because it has a small values compared to another energy balance. Okay, so this is about the formula that we will use in the air conditioning process. Let's go to the number one uh, and number two of the processes of air conditioning. That is simple heating and also cooling. Okay, as you see, all right, in this diagram, this is a simple heating where when we want to operate the air conditioning by using the heating, so we heated, okay, the coil in the duct. Okay, so the air actually in this system is heated, okay, by circulating it through a duct that contain the tubing for the hot gases or the electric resistant wire. Uh, so the amount of moisture in the air remain constant. Okay, specific velocity, specific humidity is constant. During this process, since no moisture is added to or removed from the air, so the specific humidity of the air remain constant during the heating or combustion process, so with no humidifications or dehumidification. Such heat process proceed in the directions of increasing um, dry bulb temperature, following a line at constant specific humidity on the psychometric chart, which appear as a horizontal line. Okay, as you see, this is a psychometric chart. So when it heating, it will go up from left to right, but in simple cooling, it will go for right to the left. Okay. Notice that the relative humidity of the air decrease uh, during the heating process, even if the specific humidity omega remain constant. This is because the relative humidity is the ratio of the moisture content to the moisture capacity of air at the same temperature. Okay, remember the definitions of relative humidity. That's mean phi. And the moisture capacity, okay, the moisture capacity will be increased with temperature at the heating process. Therefore, the relative humidity of heating air may be well below comfortable levels, causing dry skin, respiratory difficulties, and an increase in the static electricity. Okay, in term or in another cases or environment of simple cooling, at constant specific humidity is similar to the heating processes that I have discussed with you, except the dry bulb temperature decrease and the relative humidity increase during this process. Okay, so cooling actually accomplished by passing the air, okay, passing the air over some coil through which refrigerant or chill water flow. Okay, this is a cooling coil. We remove heat. For heating, we supply heat. Okay, so the equations, okay, the equation that can be used in these two processes, dry air balance, that means m dot air at state number 1, that means before come to the coil, is equals to m dot a number 2, okay, number 2, that means after air passing to the coil, is equals to m dot a. Okay, for water balance, omega 1 is equals to omega 2. For energy balance, only have the rate of heat Q dot is equals to m dot a H2 minus H1, or we can make it in the small Q, that means specific heat, is equals to enthalpy minus enthalpy at state number 1. Okay. All right. Let's look on the example. Okay, example of this case. A heating section consists of a 38 centimeter diameter duct that houses a 4 kilowatt electrical resistant heater. Air enter the heating section at 1 atm, 10 degrees Celsius, and 40% relative humidity at a velocity of 8 meter per second. Determine A, the exit temperature, B, the exit relative humidity of the air, and C, the exit velocity. Okay, this question actually give some of the values that can be used. Okay, first you know the heating section 1 atm, temperature 1 at state 1 at 10 degrees Celsius, and also the humidity, relative humidity 40%. Okay, this is a solution that based on what you know that has been given in the examples. So we can find from the psychometric chart. Okay, okay, I will show how to find this value we get from the psychometric chart. Enthalpy 1, specific enthalpy 1, H1, relative specific humidity mega 1, and also specific volume for 1. Okay, based on this value, okay, based on this value we get this output value from psychometric chart. How to find this value? Okay, let's go look on the psychometric chart. Okay, this is a psychometric chart. So the value mentioned 10. Okay, the temperature T1 is 10 Celsius. Okay, 10 Celsius. If you look at dry bulb temperature 10, okay, I increase. This is 10 degrees Celsius. So okay, I made a graph here. This is 10 degrees Celsius. And then another properties is the phi, relative humidity. Okay, relative humidity is 40%. Okay, 40%. This is a line of 40%. So the intersection between this dry bulb temperature and relative humidity is right here. Okay, it's right here. So from these two intersect line and curve, we can find H1. Okay, H1 is up here. This is the line of H1. So I draw H1 until I reach this one. Okay, H1 is about 15, 60, 70, 18, 90, 20. Okay, it's about 70 or 18. Okay, uh, kilojoule per kilogram. So we will get the answers of H1 is 70.7 kilogram. Okay, this is 70.7. Omega 0.003. So how we get 0.003? Okay, slide a straight line to omega. Okay, this is the specific humidity. So you sketch a straight line from this intersect. Okay, and then it will touch the value of number 3. This is 5, 0, 5, and this 2.5. This is 3. So the unit here is gram. So 3 you have to divide it by 1000. That means 0.003. Omega 1 is about 0.003. Okay, 0.003 kilogram water per kilogram dry air. That is omega. And this is equals to omega 2 because we know the cooling and heating omega is constant. And V1 specific volume is 0.8. Okay, specific volume is 0.8. This is a specific volume line. So you draw the straight line for specific volume, must be parallel with two line, right, left and right. So I draw. Okay, from here, this is a 0. Okay, okay. This is the point 8. This is 0.82. Okay, 0.80. Here is about 0.81, but the line is in between 0.80 and 0.81. So this value is about 0.806. Okay, 0.806 meter cube per kg specific volume. So 0.806 meter cube per kilogram. Okay, that is how you get these all answers values from this cytometric chart based on the parameters or properties that have been given in the question. Okay, so we have to find um, exit temperature. Okay, so based on the mass flow rate of dry air through the heating session, we know that the formula of the m dot a is rho av. Okay, rho is a density. Density is 1 over v1, small v1, specific volume, time velocity 1 time area 1. Okay, for point number 1. So we have known, or we have find a specific velocity 0.8. Okay, put the values in the formula. The velocity has been given 8 meter per second, and the area, this is a diameter 38 centimeter. So you have to find the area of this duct. So pi times d square over 4. Okay, for the area for the duct. So then the mass flow rate for the air dry is 1.126. Then from the energy balance on the air in the heating sessions, use this formula. We neglect potential energy, kinetic energy, and also the work come from the fan. So the rate of heat in is equals to m dot a time h2 minus h1. So put all the values in here, and lastly you will get h2 is 21.25 kilojoule per kilogram dry air. Then to know the exit state of the air, fit now you have H2, and also you have omega 2. So look again on the skychromatic chart, then you can find T2 is 30.5 degrees Celsius based on H2 and omega 2. Okay, let's see H2. H2 is about 21. Okay, we go to H2 21. This is 2021. Okay, 21. Draw a straight line to the 21. 21, we draw the straight line here, straight line. 20, this is 21. Omega is omega 2. What is omega 2? Omega 2 is equal omega 1. So 0.003, that's omega 2. Okay, 0.003. So 0.003. Okay, omega is here. This is omega. Okay, omega. So the intersect between H and omega. H and omega is here. All right, here. Then the temperature, exit temperature, is about 13. Okay, 13. So 13.5 Celsius. That is T2. Okay. For B the exit relative humidity and the exit velocity. Okay, the exit phi is phi2 is the 31 and phi is 31.7. How you get the 31.7? And specific velocity, okay, 31.7, this is 30%. So this is around 31, okay, this is around 31. So we get it here around 31 point something percentage for RH, relative velocity, and specific velocity is about 0.81 something. Okay, so 0.816 meter cube per kilogram dry air. Why we have to find a specific velocity? Because it will be, we want to use it for another at C. Okay, C, the exit velocity is determined from the conservation of mass energy, mass of dry air. So m dot, as I say, m dot is equal to rho av, or 1 per specific velocity, av, area. So use this formula, and then you rearrange, and then you find the exit velocity uh, is 8.1 meter per second. Okay, so in this example, we have solved all these three determination: exit temperature, exit relative humidity, and exit velocity. And the solution must, you have to know how to read the psychometric chart to solve this example or this question. Now let's look on another example. Example number 6. Okay, this is example about the process of cooling uh, process. Okay, the process of cooling system. Okay, air enters a 14 centimeter diameter cooling section at 1 atm, 32 degrees Celsius, and 30% relative humidity at a velocity of 18 meter per second. Heat is removed from the air at a rate of 1200 kilojoule per meter. Determine A, the exit temperature, B, the exit relative humidity of the air, and C, the exit velocity. So the solution for this example, you have been given the values of 1 atm, the temperature inlet 32 degrees Celsius, and the relative humidity of 30%, and the velocity of 80 meter per second. So using these two properties, that's been temperature, dry bulb temperature, and also the relative humidity, see or look on the psychometric chart to find the output of exit temperature, relative exit relative humidity, and also the exit velocity. So from the psychometric chart, the values that have been found there is H1, omega 1, and specific volume. Okay, how we can get these all values? Okay, open your psychometric chart. Uh, the dry temperature is where is the dry temperature is 32 Celsius. Okay, find the 32 Celsius dry bulb temperature. Okay, dry bulb temperature, uh, and then 30, 35, 32. Okay, this is around 32, 32, and then the relative humidity is 30%. Okay, 30%. So 30%. Here is 30%, and the intersections is between the straight line and curved line. 30% is here. All right. Okay, from there you can find the value of a specific enthalpy. Okay, specific enthalpy. Draw a straight line to specific enthalpy, and then omega, that means specific humidity. Specific humidity. Here to okay. From the chart, you can see the specific humidity is around 5 and 10. So uh, 9. Okay, is around 9 or gram. So in kilogram of water per kilogram of dry air is about 0.09. 0.09, and the enthalpy is 55. Okay, enthalpy is 55 kilojoule per kilogram. Omega or specific humidity is 0.09 or 89 kilogram water per kilogram dry air, and it is equals to omega 2 because the cooling process occur at constant omega, and the specific volume is 0.8. How I get 0.8 from here? Okay, this is specific volume. 0.88. This one 0.86. 86. 8. 86. 87. 0.87. 0.877. Okay, this is around 0.877, okay, meter cube per kilogram. So when you have obtained all these values, all these parameter values, then you can use the formula of mass flow rate of air, rho AV. From there, 1 per specific volume times velocity times area. So put all the values in these equations, and then this is a cylinder diameter. So you have to find the cylinder area, pi time d square over 4, and then you will get the m dot a is equal to 2.58 kilogram per second. Then to find H2 and specific enthalpy at point 2 or at the exit of the cooling process, from the energy balance on the air in the cooling section. So using the equations of energy balance, neglected potential energy and also the kinetic energy, and also remember to neglect the work of the fans of the system. So the Q dot out is equals to m h2 minus h1. Negative means that this is heat out, okay, heat remove from the system, so it is negative according to Chengal, okay, according to Chengal's alter books, okay, so negative q dot, so convert convert this unit to kilojoule per second, because in the example, one 200 is in the unit of kilojoule per minute, so we convert it to joule per second, and put all the values that have you obtained previously, and then you get H2 is equal to 47.2 kilojoule per kilogram dry air. So when you have these parameters H2 and omega 2, then you can find from the psychometric charts T2. Okay, H47.2, 47.2. Okay, we look H47, H47.2567.2. This is around here, 27.2. So you move this straight line, and then also the straight line come from the omega. Okay, omega. So the intersection between these two lines is in here, and you can look at here. The temperature is around 24. Okay, 24.4 degrees Celsius. That is T2. Okay, B, the exit relative humidity of the air. The exit humidity, V2, V2 from the chart, V2 is around 40, 48. Okay, 48. It's around 48, 48 percent. So it's around 48 and then 46.6%. Okay, let's see again on the chart. This is 40, 45, 46. Okay, 46 or 47 percent. That is fee at state 2. Okay, and the specific volume is 0.85. How I get 0.85? Okay, this is 0.84, 0.86, and then in the middle of these two graphs is 0.85, and then the exactly value at this intersect is 0.855. Okay, 0.856. Okay, 0.856 meter cube per kilogram dry air. So to find the exit velocity, we can use the equations of conservation of mass for the dry air. So in here, the exit velocity is determined from the conservation of mass of dry air. So using the formula of conservation of energy, m dot A is equal to rho AV. So simplify this formula, V2, okay, V2 is equals to specific volume 2 over specific volume 1 times by velocity 1. So then you will get the exit velocity is 70.6 meter per second. Okay, this is the second example, but at different conditions. The first one is on the heating process. The second one is on the cooling process. Okay, without humidifying. Okay. Okay, now we go for the next stage of process heating with humidifications. Okay, heating with humidification. Problem with a low relative humidity, that's mean resulting from simple heating, can be eliminated by humidifying the heated air. So how to do this? This is by this method by passing the air first through a heating section, then through the humidifying sections. Okay, as you see in the diagram below, okay, this is the heating section where state number one is before heating, state number two after heating, air is heated process with the heating coil, and then at state number three, this is the humidifier, and this section is humidifying section, where at this section the moisture we add moisture, okay, more moisture to the these sections. So what happened when we do this humidifications section, this will be result in humidifications with additional heating. Okay, additional heating, that means temperature 3 is greater than temperature 2. This is because the water that we spray here is a steam. Okay, is a steam. Steam is a hot water. Okay, hot water. So it will be increase the temperature 3. Okay, if we spray water, not the steam. Okay, the latent heat of vaporizations come from the air and result in the cooling of the heated airstream. That means T3 is lower than T2. The temperature at T3 is lower than T2 when we use water spray here. But when we use steam spray at this humidifying section, what happened? Temperature at T3 is greater, okay, increase compared to T2. Actually, the humidifier at the humidifying sections depend on which of the water used. Either use water or either use steam. Okay, so this is the physiometric chart. Okay, physiometric chart that show how the process occur. Okay, at first state 1 and state 2, this is the temperature going through the heating coil, and then the temperature increase at T2, but at this process omega 1 is equals to omega 2, that means constant specific humidity. And then after 2 to 3, this is the humidifying sections where steam, okay, not water, steam is sprayed here, and steam is sprayed here. What happened? The temperature is increased, okay, 25 degrees Celsius increase, At these situations, the relative humidity also increased 60% compared to the first one is only 30%. Okay, these are the formula that you can use to solve the equations. Just now add another equations for humidification section, humidifying sections. That means m omega plus mw, that means m dot w is water come from the humidifier, is equals to m dot a omega 3. So we simplify these equations, then it will give m dot water is equals to m dot a times omega 3 minus omega 2. Okay, let's see the example. So this is example 7. An air conditioned system is to take in outdoor air at 10 degrees Celsius and 30% relative humidity at a steady rate of 45 meter cube per minute, and to condition it to 25 Celsius and 60% relative humidity. The outdoor air is first heated to 22 degrees Celsius in the heating section and then humidified by the injections of hot steam in the humidifying section. Assuming the entire process takes place at the pressure of 100 kilopascal, determine A, the rate of heat supplied in the heating section, B, the mass flow rate of the steam required in the humidifying section. Okay, so to solve this solution, firstly, outdoor air is first heated. Okay, outdoor air is first heated and then humidified by steam injection. Okay, this is how it's come for the solutions. Okay, the rate of heat transfer and also the mass flow rate of the steam are to be determined. The assumption that you have to do is this is a steady flow process and the mass flow rate of the dry air remain constant during the entire process. Okay, number one. Number two, dry air and water vapor are ideal, we assume as ideal gases. And number three, kinetic and potential energy are negligible. So in here, that is some assumption that you have to consider. Okay. So this is a diagram. What happened as the example question. So T1, V1, V1, okay, has been given, and then air at T2 also have been given. This is a heating process, and this is the humidifying process where steam is sprayed at this section and then the temperature becomes 35 Celsius and the V3 is become 60%. So the graph is like that. The process occur at the psychometric chart is as shown. Okay, this one. So to solve the problem, we apply the mass energy balance on the heating section, as you see in this previous slide, as the example, as the equation that can be used in this sections or in this cooling humidifying. Okay, so based on this, we start the system actually to heating and the humidifying section. So the as I showed the schematic diagram and also the psychometric chart as shown. Now we notice that the water vapor in the air is remain constant in the heating sections. That means omega 1 is equals to omega 2. But increases in the humidifying section. That means omega 3 is bigger or large than omega 2. Okay, that you have to note this that. Okay, okay, and then you have to consider this is not 1 atm. Okay, this is 100 kilopascal pressure. So to determine based on the properties, to determine on the psychometric chart. Previously, I only show the psychometric chart that will be 1 atm. Okay, however, uh, this use a limited to specified pressure only, so which is 1 atm. Uh, so in this case, it's 100 kilopascal. Uh, so you have to find the psychometric chart 100 kilopascal. Or another way, or another choice you can do is by using the formula. Okay, as you seen or as you study previously in the part one. I think part one lecture. Okay, part one lecture. So in this case, we use the formula. Okay, you look again the part one lecture based on the sub chapter relate specific and relative humidity. Okay, based on that you will see the equations that can be used. So to find this because okay, why I use this equation, because in this case the air have dry air and also the moisture. So the moisture, the relative humidity has been increased. Okay, has been increased until it saturated air. Okay, that's why we can use these equations. So you know the formula pressure for vapor water at 1 is equals to V1 Pg. Pg is pressure at saturated air. Okay, is also Vp saturated at 10 degrees Celsius. So you also should find P saturated at 10 degrees Celsius. Okay, to find this value, uh, you can find it from the properties table. Okay, that means P saturated at 10 degrees Celsius uh, is 1.2281 kilopascal. Okay, see in table A4 in properties table. Okay, and at 25 degrees Celsius is 3.1698 kilopascal. Okay, and also the saturated water vapor or for enthalpy is 519.2 kilojoule per kg at 10 degrees Celsius, and 2541 kilojoule per kg at 22 degrees Celsius. Okay, all what I have mentioned, the numbers, the values is based on the properties table at table A4. Okay, so come back to the equations. So P saturated at 10, you know the values, then put all the value in the equation, it will give 0.368 kilopascal for P water vapor at point 1. Also, you know the total pressure if the atmospheric air is mixed with dry air and moisture. So the total pressure is a partial of dry, is partial of air plus of water vapor. So to find the pressure of dry air, is equals to total pressure minus P water vapor 1. Now is equal to 100 minus 0.368, where you have find the answer before this 0.68 kilopascal. Put in the equation, and then you get the pressure. A1 is 99.632 kilopascal. So using the ideal gas equations, you can find the specific volume at point 1 is equal to 0.85815 meter cube per kg dry air, and then the m dot a mass flow rate of dry air is velocity is volume, sorry, velocity, this is a volume, okay, rate of volume minus specific volume, so it will give m dot a is 55.2 kilogram per minute. Okay, then use the specific humidity equations. You have find PV1, P1 and PV1. So in here you will get W1 is 0.023 kilogram water per kilogram dry air. H1 is equals to CPT1 plus omega 1 Hg. These all equations you can see again in part 1, air conditioning. Okay, I have mentioned, I have discussed earlier. Okay, so H1, put all the values, and then you will get 15.8 kilojoule per kilo dry air. For H2 also the same equations, and then put the value based on point number 2, then you will get 28 kilojoule per kilogram dry air. Then to find the heat rate of heat transfer to air, so using the equations, energy balance, Q dot in, this is heating, okay, Q dot in, so M dot A delta H, so substituting all the values here, and then you will get 673 kilojoule per minute. That is for rate of heat transfer to air. To find M dot omega, okay, or mass flow rate of the steam required in the section of humidifying, use the mass balance for water in the humidifying. So this is the relationship. So m dot water is equals to m dot a omega 3 minus omega 2. So omega 3 can be found using the omega equations, specific humidity. So you get the values for omega 3, and then put this value into the equations. M dot W will give your answers to 0.539 kilogram per minute. Okay, that is the answers solutions for this example. Okay, next we go for the cooling with dehumidifications. Okay, dehumidifications is the remove moisture. Okay, cooling with dehumidification, remove water. That means the specific humidity of air still remain constant because it's a cooling process, at the simple cooling process, but its relative humidity increase. Okay, so if the relative humidity reach undesirable high levels, it may be necessary to remove some moisture from air because air has been saturated with moisture. So it must be removed some moisture, that is to dehumidify it. This required cooling with air below its dew point temperature. Okay, so the equation based on the dry mass balance, as you see earlier, okay, mass balance, mass water balance. So from here, water mass flow rate is equals to omega 1 minus omega 2. Energy balance, as I share, neglect potential kinetic energy. So you only have Q dot out equal to M dot H1 minus H2 minus the M dot W HW. So this is schematic diagram of this process. As you see here, the water, the condensate, uh, and it can be removed, and the temperature firstly at state 1 is 30 degrees Celsius, but when it this air go to the stream through cooling coil, then what happen, the temperature will be reduced to 14 degrees Celsius. And the process that show in the skyrometric chart is like this. Okay, the process, the hot or moist air enter the cooling section at state 1. As it pass through the cooling coil, the temperature decrease, okay, and its relative humidity increases at constant specific humidity. Okay, if the cooling session is sufficiently long, air reaches its dew point, that means state X. As you see in the chart, this is state X, okay, where it is saturated air. Further cooling of air result in the condensations of part of moisture in the air. So the air that's remain saturated during the entire condensation process, which follow a line of 100%, okay, here relative humidity until the final state of state 2 reach the water vapor, the water vapor that condense out of the air during this process is removed from the cooling section through a specific channel. The condensate is usually assumed to leave the cooling section at T2. Okay, that is assumption that you must consider. Okay. Actually, the saturated air at state 2 usually road directly to the room where it meets with the room air. Okay, that is the explanation what happened in the stoichiometric chart here. Okay, let's look on the example. Okay, example. So the example, the air enter a window, air conditional at 1 atm, 32 degrees Celsius and 70% relative humidity at the rate of 2 meter cube per minute, and it leaves as saturated air 15 Celsius. Part of the moisture in the air that condenses during the process is also removed at 15 degrees Celsius. Determine the rate of heat and moisture removed from the air. Okay, so the air is cool. Okay, the air is cool and dehumidified by a window air conditioner. So what you have to find is the rate of heat and moisture removed. So the assumption first you have to do is number one, this is a steady flow process, and mass flow rate of dry remain constant during the entire process. Number two, dry air and water vapor are ideal gas. Okay, that is assumption you have to know. And kinetic and potential energy are negligible. So at this situation, of course, it is deal with saturated air. So the enthalpy of saturated liquid water at 14 degrees Celsius is 58.8 kilojoule per kg. So this enthalpy value, you can take it from the properties table in table A4. Also, inlet and exit states of the air are completely specified, and total pressure is 1 atm. Therefore, you can use these properties, or you can use the psychometric chart to find H1, omega 1, V1, H2, and omega 2 based on the stoichiometric chart lah. Okay, by using T1 and Phi1, you get all H1, omega 1, V1, and then from there T2, Phi2, you will get H2 and omega 2. Okay, as I show you how to use the psychometric chart. So now you try do it yourself and get this answer. Okay, so then you also can find H omega is equals to H fluid at 15 degrees Celsius is 62.982 kilojoule per minute. This is taken from the properties table in properties table. Properties table, that's mean in table A4. Okay, for water. So the mass flow rate, you can use the formula rho AV. So simplify that formula, then you will get the answer is 2.238 kilogram per minute for m dot air 1 at state number 1. To find m dot w at the dehumidifying sections based on water mass balance, use this formula, then m dot w is equal to 0.0233 kilogram per minute. And then to find the rate heat out from this system, so based on energy balance, then you get the answers of Q dot out is 97.7 kilojoule per minute. Okay, that is for Q dot. Therefore, that means after you have conclude or get the answer, that means this air conditioning unit remove, okay, this remove moisture and heat from the air at rate of 0.131 and 551 0.131. So okay, now we go for the next subchapter is about evaporative cooling. Okay, evaporative cooling. This is some knowledge that you have to know. Evaporative cooling is also known as a swamp cooler. So based on the principle, what is evaporative cooling? As water evaporates, okay, the latent heat of vaporizations is absorbed from the water body and surrounding air. Both water and air are cool. Practical approach where we can see this evaporative cooling. Air feel a lot of cooler when the yard is watered. Okay, this is how we can see the practical approach. Hot air, that means enter the evaporative cooler, spray with the liquid water. So water come out from the injector, okay, and then at that situation it have a hot air. So part of the water evaporate and then absorbing heat from the airstream. Okay, at situation that will be absorbed to the water. Airstream temperature decrease, humidity increase, and then uh, adiabatic saturation process where heat transfer between air stream and surrounding negligible. Okay, so we use the adiabatic saturation. So the heat transfer between air we and surrounding we negligible. So we assume that T wet bulb and enthalpy is constant. So this is the example the in desert, that's mean hot and dry climates, we can avoid the high cost of conventional cooling by using evaporator cooler, also known as a swamp cooler that I have mentioned. Here water, okay, example you see at the jug here, water that leak out, hot and dry air. So water in the porous jug left in an open breezy area cool as a result of evaporator cooling. These examples. So the process is essentially indicator to adiabatic saturated process. Okay. So what is constant here? Wet bulb and also entropy is constant. And if you see in the skyrometric chart, this is where TWB and his is constant. Okay, hot dry air. Hot dry air is through the humidifier, and then cool moisture air come out here. This is what happened in evaporator cooling. So this is a picture about evaporative cooling. More humidity, swap stay on the screen, uh, limit to no relief from the heat. So less humidity, what happen? Swap evaporators. Okay, more relief from heat. Okay, if more humidity, we are less swap. So this is some of the device that create evaporative cooling. And this one evaporative cooler, uh, it have a spray, okay, cool spray from home, and then it pump water and spray to the fan or cooler. Like domestic industrial also have, that means we use water as a evaporate, okay, evaporate in the stream, in the air. Adiabatic mixture airstream. Okay. Many air condition applications require a mixing of two air streams. Okay. Why? This is particularly true for large building, most productive and process plant, hospitals which require the conditions air be mixed with certain fraction of fresh outside air. Okay, that's why it's named as a adiabatic mixing airstream. Okay, so as you see in this schematic diagram or figures, it has two inlet and one outlet. The first one has specific humidity omega 1, omega 2, and mixing section is in between inlet and outlet. So then the output is omega 3. The formula that we will use, because this is a flow, steady flow, so mass of dry air is in is equals to out, okay, and then mass of water vapor, of course, in is equals to out, so in is 1 and 2, out is 3. Energy is the same, in is equals to out, that means 1 and 2 plus is equals to state number 3. So by these three equations, we eliminating m dot a3 from these three equations. We will obtain one of the useful formula, that means omega a3, sorry, omega a1 over omega dot a2 is equals to sorry, not omega, okay, my mistake. M dot A1 over M dot A2 is equals to omega 2 minus omega 3 and omega 3 minus omega 1, or H2 minus H3 per H3 minus H1. Okay, when these two extremes of state 1 are mixed adiabatically, the state of the mixture lie on the straight line connecting to two states. Okay, to understand this theoretical, let's look on the example. Saturated airlift wing the cooling section of an air conditioned system at 140 Celsius at the rate of 50 meter cube per minute is mixed adiabatically with the outside air of 320 degrees Celsius at 60% relative humidity at a rate of 20 meter cube per minute. Assuming that the mixing process occurs at the pressure of 1 atm, determine A, B, C, D. That means mixture specific humidity, mixture relative humidity, mixture dry bulk temperature, and also mixture volumetric flow rate. Okay, same because it use 1 atm pressure. So as a from the psychometric chart, using using what has been given in in the question, using at state number 1, you use T1 is 14 degrees Celsius and V1 is 50 meter cube per minute. So from there you will get H1 omega 1 V1. Okay. For H2 omega 2 V2, you use T2 is equals to 30 Celsius at dry temperature, and then V2 is 60 Celsius, sorry, 60%, and V dot 2 is 20 meter cube per minute. That is all the value that you can use to get H2 or omega 2 and V2. Okay, and then from there, the mass, that means the formula that have in the formula of mass flow rate, m dot a v dot 1 over specific volume 1, so you get now 60.5 kilogram per minute. Same as m dot a, you will get 22.5 kilogram. Based on energy balance here, m dot 3 you will get 83 kilogram per minute. And then to find the humidity, specific humidity and enthalpy, use the formula that I have mentioned in the previous slide. So M.A1, M.A2, using these two formula, then you will get W3 and H3. Okay, W3 and H3. Okay, from this W3 and H3 back to the psychometric chart, then you will get T3 and P3, 90 degrees Celsius and also 89 degrees Celsius. And at the same time, V3 at psychometric chart will give 0.844 meter cube per kilogram. So from there, using the formula to convert it back to meter cube per minute, so use this formula, then put the value, then you will get 70.1 meter cube per minute. Okay, so we have covered all the only one objective, but have a lot of contents in one objective. So you have covered four processes of air conditioning processes. That's mean heating, simple cooling, and humidifying and dehumidifying. Okay, top of that, you also study or been given discuss about adiabatic mixing airstream. Okay, so that's all for today class. uh, Thank you very much for watching, and hopefully you do more exercise and read more based on the reference book. Okay, so that's it for today. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Thank you. Terima kasih.